And hello, everyone. My name is Mindy Ratcliff, and I'm really excited to be here in New York City at GopherCon with all of you. And I also want to say I'm so glad that we have some of our team from Bayer here. I know some of them are over here, some are over there, so hey guys. So today we're going to discuss making quick and effective data pipelines with Go generics. So before we get started, let's share a few details about me so you know who's up here talking and why. I was an English teacher for nearly a decade, and about 5 years ago, I decided to switch careers. And I've been with Bayer Crop Science for 3 years now, and in my professional life, I value communication, creativity, and empathy. I love working with others and finding solutions to life's troubling problems. And aside from work, I'm a mom and a yoga teacher. And here on screen, you can see my two office mates, Miso and Chu. They faithfully attend stand-up with me every day. So, oh, by the way, this is my second GopherCon, so. All right, now that I've paid my dog tax, I can proceed. Let's take a look at our agenda. First, we're going to get a lay of the land, what it's like in crop science. I want to give you a bit of insight into what it's like working in agricultural technology, and I suspect you'll see some parallels to your own industries. Then, we will look at the specific challenges we face when we build data pipelines. We will see how, without careful planning and forward thinking, our data pipelines can become rigid and not reusable. We'll discuss how we use Go generics to solve this problem. And my goal is to inspire you to look closely at how you craft your data pipelines, separating your infrastructure from your business. And you're going to see some code examples. Now, it's less about the code itself. It's just more for you to think about the concepts that that code represents. I mean, I can't show you our actual prod code, right? Let's go to the next slide. So the crop science landscape. What we do in crop science, most basically, is we plant, we harvest, and we analyze. Our data derives from fields, labs, and controlled environments. And that translates to a massive amount of data to handle. Now, on our team, we're responsible for the data pipelines which drive products through our crop science business from research and development to product supply and into the commercial space. The data we handle measures the efficacy and effectiveness of seeds we sell to farmers. It can measure anything about seeds. It can be about the soil that you plant them in or the treatments that you give them so that they don't get infected with different diseases, different fungi. And this data forms the sources that we use in our data pipeline examples that you'll see, okay? So we ingest that data, we transform it, and then we store it or ship it out somehow. In short, this translates to a lot of data in, transformation, aggregation, pushing it through our calculations engine, and then shipping that data out. Our team of 18 individuals is responsible for 36 APIs for massively scaling distributed systems and 23 asynchronous message processors. Over 100 internal services interact with our APIs, so it is a pivotal point in the crop science R&D pipeline. Now, on top of all of that, sounds fun, right? On top of all of that, we have periods of time during the year when we harvest, okay? Harvest increases our data throughput. For 3 months, if you take a look at the chart up on the screen, for 3 months we plan what we're going to plant. Then for 3 to 4 months, those seeds have to grow, right? We spend about a month harvesting those seeds, And then we have a week of advancement. Advancement is the time when we determine which seeds are good and which seeds are less good. And we only have 1 week to get those good seeds to the other side of the world for the next planting season, because there's harvest happening all over the world all the time. Our calculations help us determine the best seeds to keep growing, so then we can sell those seeds to farmers. I'm sure you probably weren't expecting farming to be so stressful, but it is. And with advancement and business needs pushing us to our maximum and continually needing to add more services or updating existing ones to meet the needs of our data scientists, our business partners, we often have to deal with rapid changes. We need services that expand in scope. We need each engineer on our team to be able to develop a new service or make adjustments very quickly. We need flexible pipelines that can handle new operations. We must expect the unexpected, especially during harvest and advancement. Now, to recap those challenges, let's boil them down. They most basically are this. We have a vast array of data sources, different seeds and their inherited qualities, different treatments to those seeds, various environmental conditions. We have to have maintainability to continue to transform and store our data. Most of all, how can we easily maintain those services during a hectic time like harvest? The world's on fire. We need really clear ways to debug our services, so if they go down, we can solve that problem as fast as possible. We need a solution where we can add new functionality or features. Our business needs may quickly pivot. Suddenly we need to add something else, some other observation. And we need efficient solutions for adjusting those data pipelines. Now, if I suddenly need to add a new step in our data pipeline that ingests, we'll say, soil data, because there is data for soil too. How can I do that with minimal friction and delay? What if there's a new observation and it's super important to the advancement of the seeds? I need to get that data to the right place with the right observations. And how can I do this without ending up blocking R&D? Everything is fine. I'm not stressed. You're stressed. Farming's fun. So, what do we need from a data pipeline? I like breaking things down and making them simple. In its most basic form, we have a source, or soil sample, whatever that might be. We ingest it, we process it somehow, and then we ship it out or store it, right? Like, that's what we do. Let's take a look at one way I could put this together with just a simple representation. Like I said, our source here is going to be that soil sample I've been talking about. And we're going to see what an MVP would look like. So, our source is the soil sample. We ingest that. We maybe stream the soil samples. Maybe we're filtering out like nitrogen or something like that. We're going to transform it to a report, and then we're going to save it. Again, this is a simplistic representation. In the next slide, we're going to take a look at how these functions might look. Okay, hopefully that is clear for everybody. Now, this is an example of how I could put this together as an engineer assigned an issue to start something. Maybe in some cases, this is how things have been developed before. It's a simple Go pipeline. It has some functions, a struct for holding our source, some channels. What you may not notice is that this is going to end up causing problems for us in the future. For our use case, with our data, it's not going to work. There's going to be some problems. So, starting at the top, Stream soil samples has hard-coded output. It's locked to a soil sample, only a soil sample. What if I need to add a new data point, like a treatment to the soil? I'd be rewriting this. We're mixing some business and infrastructure logic. Filter low nitrogen has a very specific property from a very specific type. It's not reusable, and you know people will be copy pastaing and then making more of these. It's just copy pasta crimes waiting to happen. Transform to report, it could be worse. I mean, it's a simplistic representation of making output for storage. Maybe in a real case, we might send this off to database or something like that. However, this only works for a soil sample, and that's the point I want to make. Turning into a specific type, a soil report. So only soil sample to soil report. It's hard coding that transformation logic, and it's mingling it with channel writing logic, and it's going to be impossible to reuse. Now, save reports is, again, just more copy pasta crimes waiting to happen. It's all totally bound to one type. Now, over on the other side, on this side here, we have a portion of the main function that I wanted to highlight. It's not the whole thing, but this is the part that I wanted to focus on. This is the rigidity that I've been talking about. There's a lot of room for error with those Go routines, and the second you want to handle multiple input types, or add logging, or a new batch process, it could break. We have some tight coupling here. This is hard coding all of our values. And hard coding works for when you're just getting started, when you're in the ideas phase or first iteration. But that's as far as you will go. Hard coding gets you started, but it ultimately gets you stuck. Effectively, we've hard coded ourselves into a corner. We have no reusability. To make any changes at all, we're rewriting or making new functions that are tightly coupled to the newly introduced types. There's no separation of concerns. Our business needs us to be fast and flexible, not rigid and fragile. We don't need to be bogged down rewriting these things just because we've skimped on building a solid infrastructure. Now, does this model work? Yes, it does. But for us, it doesn't. We're going to have many pain points. Now, there is an easier way with a bit of investment up front. Our team decided to work smarter, not harder. Cliche, right? Our senior staff engineer, James Wilson, decided to consolidate our pipeline functionality into an internal package for maximum reuse and a clear separation of concerns with our business logic. With it, you can build out a pipeline with everything you need, start and finish, adding in batching, streaming, transformation, all in the middle. It's like building a sandwich. All that's needed is to pass a function and create some handlers. No rewriting, and it's compile time safe. When Go introduced generics in Go 118, generics gave us the ability to write code that works with any type, since the parameter is decided later when the function or type is used. We like this because it focuses on reusability, type safety, and abstraction. We focus on the behavior over the implementation details. Now let's see how this might look. Going back to our problem, we have a source, we ingest it, we transform it, we store it, right? And yes, that is a gopher that I designed to look like Macho Man Randy Savage because he's our team mascot, okay? I'm quite proud of it. I'm an artist. All right. So, in our new model, we have the pipeline generics there to handle the operations. Well, we still have our source, the soil sample from before. Let's look closer. Here is a general look at our pipeline package broken down to its most basic parts. I just want you to get a sense of it, how we set this up. First, we have some generic handlers using type parameters. We can plug in whatever we need. They work with any input or output, whether you're processing strings, structs, protobuf, the same pipeline logic applies. Then we have our feed struct, which serves as a connecting link. Now our start function, this is how we kick it off. This is a function that is going to read data from type T from a source. Could be Kafka, a file, a soil sample, right? It has context propagation, tracing, and structured logging. There's a channel for streaming data, and it has context for each read, the pipeline name and the actual data. The start func is the engine of the pipeline. And when invoked, it logs the start, enters the loop to read data using the handler, wraps it in a span, and sends the data into a channel. If the context is canceled, it exits. It returns a function and a channel, making it very composable. Next up, we have pipe. This is one of our links in the chain. This is what will stream the data through processing. It spins up a Go routine, reads the input, passes the data to the handlers, and ships it out. It returns a run function to execute the stage, and a channel with the feed with the transformed output. This allows us to decouple the processing logic from the channels. Each stage is type safe. You can chain multiple pipe stages together and get really crazy with it. You could even have batching. Now, I have our end function and a couple extra functions up here. With our end function, it's the last stage. Consumes a channel of data in the feed struct and processes it using a handler. It returns a function, and when called, drains the channel and applies the handler of each item. With start, they bookend it. Like I said, it's like a sandwich. So start reads and emits data and consumes and processes it. And then over here, I threw some generic little utilities here. That's where you might throw in your batching or something like that. Now, these are the side-by-side representations. So we have a before and we have an after. It's like a makeover. Let's see how this looks. In the after, we have our soil sample pipeline using the pipeline package with generics. We have a start, 2 pipes chained together to transform and filter, and then a pipeline on the end. Then we have our messy before that was hard-coded and was going to give us grief. But that little bit of work invested up front really helped us in the long run. So when we put them side by side, you can see how composable this is for our use case. If we need to add functionality, we just pop in another pipe. It's that easy. It's sort of like choose your own adventure, but with data pipelines. So why do we love this? It's highly reusable. It handles the streaming or batching, transforming. It decouples error handling. And we have a clean separation of concerns. We often value strong types and explicit code. Generics let us abstract behavior without sacrificing clarity or performance. Now, remembering those challenges from before, I'm bringing them back. Let's take a look at those challenges and see how we've addressed them. So remembering we have all sources of data coming from different places, fields, labs, what have you. We need something that is easy to maintain with good debugging. We need something that can handle fluctuating business needs, and we need something that can grow with the needs of our stakeholders. Did we do it? All right, how does this accomplish that? The pipeline doesn't care what the data is, just that it satisfies the input type. We don't have spaghetti code, no tightly coupled logic, mixing our business logic, all those specifics about the soil samples. That's not getting mingled in with our Go routines. If our business needs another attribute or type, no big deal. We add a new handler rather than rewriting code. The pipelines are channel-based, so it's easy to add more channels just by using pipe with the built-in Go routines. And with feed passing through each stage, we're able to get a clear insight into each step in the pipeline. We can solve problems and identify errors much more quickly when we have that insight. The solution is idiomatic, simple, performant, and extensible. It makes building new pipelines easy, and it makes adjusting existing pipelines much more straightforward. It provides a way that everyone on the team can swiftly add a new pipeline or throw in more details about I don't know, a soil sample, right? It's worth the time to invest up front so that even junior engineers all the way up to senior engineers are just as empowered. Most of all, we can grow our data pipelines. I'm about to get really cheesy here. We can grow our data pipelines rather than constantly cutting them down and planting new ones. Lastly, most of all, we aren't fighting the language, we're leveraging it. So in summary, using generics and building an infrastructure to go faster in the long run is worth it. We don't have time for dealing with hard coding problems during harvest. Now, I might be the person who's up here talking, but I just want to say that this is our team, and this solution would not exist without them. They have made my life easier, and we work well as a team. I also specifically want to call out Tom and Cassie and Casey, who are on this, and say thank you for being you, and to everybody else from Bayer who's here at GopherCon. I'm very grateful for this team and to all of the amazing people on it, and I'm very proud to be part of Bayer Crop Science. Now, thank you all so much for your time, your attention, my corny jokes about planting things. Please feel free to connect with me on LinkedIn or email me anytime. All of the example code, if you really want to go into a deep dive, is listed in this repository. Let me know if you have any questions or any feedback. I would love to hear it. And I want to say thank you to all of the organizers, Heather, Johnny, everybody. Thank you so much. And let's all go enjoy New York. Go first. Thank you.